Hi guys, this is our third lesson for this unit, and today we're going to talk about sound waves. So sound waves are different, or I guess more specific is a better way to put it, than other types of waves, and we use them obviously all the time. So we're going to look specifically at how they work today. So sound is a traveling oscillation of atoms or pressure. So we've already talked about the word oscillation. That oscillation means moving back and forth in kind of a pattern. And if you look at the diagram down at the bottom of the slide here, you can see how sound waves, the energy is moving through atoms, either in the air or if it's underwater, it could be in water. Sound can travel through solids, liquids, and gases. But what happens is when a sound wave is created, the energy from that sound wave creates vibrations and it pushes these atoms of whatever the medium is, it pushes them into areas where they're really close together, followed by areas where they're kind of far apart. And you can see that in the diagram down there, that kind of pattern. Um, a big characteristic of sound is pitch. Pitch has nothing to do with how loud or soft a sound is. Pitch has to do with how high or low a sound is. So, to be really stereotypical, women's voices tend to be higher pitched than men's voices. And they could be talking at the exact same volume, but one sounds a little higher than the other. And what creates pitch, that's called frequency. So we've already talked a lot about frequency in our study of waves. Frequency is how many waves are occurring in a certain amount of time. If you're looking at a picture of a wave, you simply count how many crests or how many troughs you see, and that can tell you if they're close together, you've got a higher frequency. So the higher the frequency, the higher the pitch. So when you look at a sound wave, you can kind of tell from like a drawing of the wave how high or low pitched it's going to be just given the frequency of it. I'll let you actually just kind of read that on your own if you want to. It just talks about what humans can hear. We hear multiple frequencies at the same time, and then our brain interprets those frequencies and turns them into sounds that make sense to us. The loudness of a sound, just how, how much volume and energy a sound has. This has to do with kind of amplitude. The higher amplitude, the more energy the wave is carrying, the louder it's going to be. But I really want to talk, because we all understand how loud something is, I want to talk about decibels. When we measure sound, we measure it in decibels. We can actually put a number on it and say that a sound is this many decibels big. So if you look at our picture over here, our graph over here, a whisper is about 10 decibels. A normal conversation is about 65 decibels. When I am talking in class to all of you at once and I get a little bit louder than I would if it was just me talking to one other person, that's going to be a little bit louder. Traffic, if you're walking around the city and you got cars, that's about 70 decibels. And then over here, we've got a rock concert, or probably close to how loudly you all listen to music in your earbuds. That's about 110 decibels. And here we've got just some more. You can pause it if you want to and look at all these different decibels, and it just gives you some examples of how loud things are. But I want to focus on this last one down here at the bottom, 120 decibels. That's the threshold of physical pain. So when people tell you not to listen to your earbuds too loudly, you'll damage your hearing, you actually really will, because your ears, the organs inside your ears, and we're actually going to look at those a little bit later, but the organs inside your ears are not meant to take on that much energy. The waves, if they're too loud, if their amplitude is too big, then they've got too much energy. And when they hit your ears, they'll damage those organs because they're not meant to be hit with that much energy at one time. And it can be really, really painful. All right, so the speed of sound. Sound usually travels through air, right? Usually when we hear sounds, it's traveling through the air. We already talked a little bit about sound as a mechanical wave. It cannot travel through empty space. It has to travel through a medium. So usually it's traveling through air. When it travels through air, it travels at about 343 meters per second. So think about a meter stick. We used those for our Slinky Lab the other day. A meter stick. Sound can travel 343 of those in one single second. That is about 660 miles every hour. So think about how big a mile is. Sound can travel 660 of those every hour. It's pretty fast. It's not as fast as light. Light can go much faster than that, but sound is it's really fast. It travels through most liquids and solids faster than air, actually, which sounds kind of strange because we're so used to hearing sound through air. We don't really think of it as traveling through liquids and solids. I'm sure, however, that you guys have been playing around in a swimming pool and you've played that game where everybody goes underwater and you say something and everybody else tries to guess what you say because it sounds all muddled and weird. Sounds aren't clear through water or through solids, but we can hear them. You can put your ear to a solid door and hear what's happening on the other side, even if you can't hear it clearly. And the reason that it travels faster through liquids and faster through solids is because sound is traveling by pushing particles around. There are simply more particles closer together in liquids and solids than there are in air. In air, the particles are pretty far apart, so sound travels a little bit more slowly. But when you turn into a liquid, when you turn into a solid, and those particles get closer together, sound can travel faster. And over here, we've got a little diagram of that to show you kind of how fast it moves through different mediums. So, a sonic boom. This is just kind of a fun little trivia fact about sound. Um, we talk about sonic booms mostly when we talk about airplanes, when things or rockets for that matter, when we talk about things breaking the sound barrier. It's called supersonic. And what's happening, you can see it in the picture down here, when something moves faster than the speed of sound. So when you have a rocket or you have a jet and it's actually flying faster than sound, it squishes up those sound waves, it gets ahead of those sound waves, and we end up with this weird shock wave forming where everything kind of just piles up at once. And then we hear that when it gets to us as a huge sonic boom. Now, sonic booms can really damage your hearing. They're very, very, very loud. But that's what's happening there. Something is breaking the sound barrier. It's moving just a little bit faster than sound and causing all of those sound waves to get squished and pile up, which sounds to us like one huge boom. Just a little interesting fact about sound there for you. The wavelength of sound. So some waves are microscopic. If you were to actually measure from one crest of a wave to another crest of the wave, they'd be tiny. Some are really huge. Some waves have wavelengths that are miles long. Sound is kind of just an ordinary in the middle. So if you look over here at this chart, we've got frequencies here, and it shows you how many meters or centimeters apart those different sounds are. So let's look at bass guitar right here. When somebody is playing a bass guitar, those sound waves, each wavelength, each crest is only about 3.5 meters, 3.4 meters apart. So 3.5 meter sticks, right? So sound waves, the actual waves themselves, even though you can't see them, they're there. And they are usually just normal sized, the size of everyday objects. And there's a graph, just in case you were curious. You can pause it and look at it if you want to. All right, so now let's talk about standing waves. So sometimes we have waves that are confined in a space. The sound wave isn't just floating around wherever it wants to, it's actually confined to a certain space. And that's called a standing wave. So think about a guitar string. A guitar string can create a sound wave, right? But it cannot move around independently. It's stuck on the guitar. There's only a certain range of motion. There's only so much space it can move around in. So when I pluck a guitar string, it creates a standing wave. And it's kind of an oscillator because when you pluck that string and create that wave, it moves back and forth. The guitar string actually moves back and forth, right? So, if you have a guitar string that's moving back and forth, it's creating multiple waves. Every time it goes up and down, that's kind of a new wave. So when you have those two waves that combine at the right place, when they combine in the middle, it looks like the string of the guitar is standing still, even though it's not. And this works for any stringed instrument. It works for a slinky. If two people are holding a slinky, that's a standing wave, right? Because it can only go from one person's hand to the other. It's not free to go wherever it wants. And when you both move the slinky back and forth, if you are both kind of pushing it back and forth, you're both creating waves. There are places of the slinky where it looks like it's not moving at all, right? And that's because those waves are equal, but they're canceling each other out because they're coming in the opposite direction. So I saw a lot of you all when we did our slinky lab do that, kind of just play around with it back and forth. So I'm sure you kind of have a picture in your head of that. So let's talk about how we can describe those. So standing waves. The lowest natural frequency when you don't have very many waves happening at all. So that would be picture number 1 here. I only see one big wave. That's called the fundamental. That's kind of your basic wave. However, waves 2, where you divide it up into 2 waves here, wave 3, there's 3 waves here, 4 and 5, okay? Those are all called harmonics, and they're going to act the same. So for sound waves, that means they're going to sound the same. This is where we get the word harmony from, but they're just on a different frequency. So kind of they sound the same, just higher or lower because they have a different frequency. So this would be like one whole guitar string, but if I put my finger in the middle of that guitar string and plucked it, okay? Or you could do the same idea with the slinky if you can picture that in your head. So, one more time back to the slinky or guitar string, whichever is easier for you to picture in your head. When you pluck it and it's oscillating back and forth as that wave is moving back and forth, the edges where you're holding it, if you're both holding a slinky, the edges up here at the very top where my mouse is and down here at the very bottom, those are called nodes. And the node is where it doesn't seem to be moving at all. You're holding it still there. So on a guitar, this would be the very end of the guitar, and then right at the top of the guitar where the strings are attached, where they don't move at all. Something's holding them still. Those are called nodes. The antinode is right in the center where you've got the greatest movement. It's really pulling away from either the middle of the slinky or from the guitar there. Okay, so to measure the wavelength of one of these types of waves, you just want to measure 2 harmonics, 2 crests, from crest to crest. And then the last thing we're going to talk about is beats. So when you have 2 waves that have 2 different frequencies and they're not exactly equal, they get in each other's way, they sound kind of messy, but to our ears, it starts to pulse. It starts to sound like a beat. So now obviously if you're listening to a song and you've got drums, they're creating that beat. But sometimes if you just hear a really long whistle or you hear like maybe a siren, those sounds, there's no actual drum there, but you still kind of feel or hear a pulse or a beat. And that's because you've got 2 different frequencies happening at the same time. And they combine down here, like you see, to make a really complex wave. It looks like the wave that you graphed where it's all funky and weird. And that's what's creating that kind of beat that you're hearing. And there is a picture of that. The very last thing I want to talk about is the Doppler effect. So we already talked about this a little bit in our space unit, but just one more time, the Doppler effect talks about how we hear sound waves differently when the thing that's creating the sound wave is moving. So let's say you've got an ambulance, it's got a siren blaring. Okay, if I'm in front of it, the closer it gets to me, obviously it's going to sound louder, but it's also going to sound higher pitched because the frequency gets closer as it gets closer to me. If you're behind it and it's moving away from you, the exact opposite's going to happen. It's going to sound lower because the frequency as it pulls away from you is going to kind of stretch out and the pitch is going to get lower. And there is your graphic of that. All right, so that's sound waves. You've already kind of had an introduction to them, and they're pretty simple. We're going to talk about all this in a little bit more detail in class, so I will stop talking because this video has gotten a little bit longer than I told you most of them would be. So your vocab word of the day, go ahead and put it into Google for me. It is the Doppler effect. Tell me what the Doppler effect is in Google Classrooms, and then we'll talk about sound waves. All right, see See you tomorrow, guys.